Today I'll talk about fluid mechanics summary, fluid properties. Summary of fluid properties. Fluid means a liquid or gas or mixture of both. It can be defined as a substance that deforms continuously under the action of external shearing force. The continuous deformation of the fluid is called flow. Now what is the first you have to understand standard temperature and pressure STP. At STP, pressure is 760 mmHg, temperature is 0 degree centigrade. And NTP, normal temperature and pressure is 760 mmHg and temperature is 20 degree centigrade. The study of the behavior of the fluid at rest or in motion is called fluid mechanics. The study of fluids at rest is called fluid statics. The study of fluids in motion without considering the pressure or cause of motion is called fluid kinematics. The study of fluids in motion while considering the pressure or causes of motion is called fluid dynamics. Fluid dynamics. Next is density. Density is nothing but we can denote as a rho. Rho is the density of the fluid. So that is nothing but mass of the fluid by volume of the fluid. Density of the water is 1000 kg per meter cube at 4 degree centigrade. Density of mercury 13,600 kg per meter cube at NTP. Density also known as mass density. Specific gravity SG. The specific gravity of substance is the ratio of its density to the density of a reference substance, usually water at a specified temperature. SG is equal to density of substance by density of reference material. Means density of substance by, generally we take the reference density as water density. Then specific weight gamma. The specific weight of a substance is the weight per unit volume. That we can write gamma is nothing but rho into g, where rho is the density and g is the acceleration due to gravity. Specific volume. The specific volume of a substance is the reciprocal of its density. It represents the volume occupied by unit mass of substance. That small v is equal to 1 by rho, where small v is the specific volume and rho is the density. And density we already talked about that, mass by volume. Now here I am talking about two forces, adhesion and cohesion. Adhesion is the attractive force between molecules of the different substance. It causes liquid or gas to stick to a solid surface. Cohesion is the attractive force between molecules of the same substance. It causes liquid or gas to stick to itself. Adhesion versus cohesion. In general, liquid are often dominated by cohesive forces, while gases are dominated by adhesive forces. Liquid tend to have higher cohesive forces due to the closer proximity of the molecules, while gases exhibit more significant adhesive force with nearby surface. Now I'm talking about viscosity, Newton's law, and shear stress strain relationship. Viscosity is a measure of fluid's resistance to deformation or flow. It is a property arising from the internal friction between fluid layers as they slide past each other. Newton's law of viscosity states that the shear stress tau between adjacent fluid layer is directly proportional to the velocity gradient du by dy in the direction perpendicular to the layers. Tau is equal to mu du by dy, where tau is the shear stress, mu is the dynamic viscosity, du is the change in velocity, and dy is the distance between layers. Now shear stress and shear strain relationship. The relationship between shear stress and shear strain is given by tau is equal to mu dot gamma. Gamma is nothing but du by dy, where gamma is the shear strain. Now unit in MKS, SI and CGS system. So viscosity unit MKS system Pascal second, SI unit also same Pascal second, CGS unit poise, that is nothing but gram per centimeter second. That is very important. Then centipoise. The centipoise is a common unit of viscosity. So 1 Pascal second is nothing but 10 centipoise. So 1 poise is equal to 100 centipoise. Conversion between MKS, SI and CGS. To convert viscosity between MKS and CGS, so 1 Pascal second is nothing but 10 poise. MKS and SI are equivalent in viscosity measurement. Then coming to the kinematic viscosity. Kinematic viscosity is the ratio of dynamic viscosity to the density. It represents the fluid resistance to flow under the influence of the gravity. So nu is equal to mu by rho. So here mu is the dynamic viscosity, nu is the kinematic viscosity, and rho is the density. Now what is the unit of the kinematic viscosity? MK system kinematic viscosity unit is meter square per second. SI unit are same. SI unit is also same, meter square per second. And CGS unit centimeter square per second. Now centipoise and centistoke. Centipoise is a unit of dynamic viscosity and centistoke is a unit of kinematic viscosity. There is no direct conversion between them as they represent different properties. To convert kinematic viscosity between MKS, SI and CGS, so 1 meter square per second is equal to 10 to the power 4 centimeter square per second. MKS and SI are equivalent in kinematic viscosity measurement. Now coming to the fluid types. Fluid can be categorized in three ways: ideal, perfect and real. So ideal fluid is a theoretical fluid with no viscosity. It is assumed to be a compressible. The flow is described using the Eulerian equation, primarily used in theoretical analysis. Perfect fluid, similar to an ideal fluid, may include additional assumption, may assume the absence of heat conduction and diffusion, characterized by an equation of state relating pressure, energy, density and temperature, used in relativistic physics to model certain properties of matter. Real fluid refers to fluid that exist in real world, exhibits properties such as viscosity, compressibility and thermal conductivity, doesn't conform to the idealized assumption of ideal or perfect fluids. Example includes water, air and oil etc. So I can give one example. Consider the flow of water through a pipe. If we assume no viscosity and incompressibility, we model it as an ideal fluid. In reality, water has viscosity and is compressible, making it a real fluid in practical situation. Now coming to the Newtonian and non-Newtonian fluid. Newtonian fluid. A Newtonian fluid is a type of fluid that follows Newton's law of viscosity. The shear stress between adjacent fluid layer is directly proportional to the velocity gradient in the direction perpendicular to the layers. So tau is equal to mu du by dy, where tau is the shear stress, mu is the dynamic viscosity, du is the change in velocity and dy is the distance between layers. Example: water, air, most common fluids. Now shear stress and deformation rate relationship of the different fluids. So here two plates are there. So one plate is here, top plate. So top plate is moving and bottom plate is stationary. Now when we apply force in the top plate, so now fluid will deform and we can express that deformation, and due to the deform fluid will flow. That flow as in the bottom plate is stationary, so velocity adjacent to the plate is adjacent to the plate, mean velocity of the fluid adjacent to the plate is 0 and fluid velocity as u at top plate is moving. So from there we can derive equation, or we can say tau is equal to mu du by dy. Now non-Newtonian fluid. A non-Newtonian fluid doesn't follow the Newton law of viscosity. The relationship between shear stress and shear rate is more complex, classified based on behavior under shear. Now here three types: shear thinning, viscosity decrease with increased shear rate, that is SketchUp. Shear thickening, viscosity increases with increased shear rate, that is corn starch and water mixture. Viscoelastic, exhibit both elastic and viscous behavior, that is polymer solution. Now example: non-Newtonian fluid. Consider the flow of a ketchup, that is shear thinning, and corn starch and water is shear thickening, to illustrate non-Newtonian behavior. Now again, non-Newtonian fluid are classified based on their behavior under shear stress and shear rate. Pseudoplastic, shear thinning, viscosity decrease with increasing shear rate. Dilatant or shear thickening, viscosity increase with increasing shear rate. Bingham plastic exhibit a yield trace below which no flow occurs. Plastic behaves as a rigid body until a critical trace is exceeded. Thixotropic, viscosity decrease with time under the constant shear stress. Rheopectic, viscosity increases with time under constant shear stress. Now here shear stress and velocity gradient relationship expression. So for pseudoplastic, tau is equal to k du by dy to the power n, where n less than 1, and dilatant tau is equal to k constant du by dy to the power n, where n greater than 1, and Bingham plastics tau is equal to tau 0 plus mu du by dy. For tau du by dy, velocity gradient greater than 0, otherwise tau will be 0. Now here is the flow behavior index and k is the flow consistency index. Now here shear stress deformation rate relationship of different fluid. So Newtonian fluid for high viscous, okay, so that Newtonian fluid follow the Newton law of viscosity, and other are non-Newtonian fluid like Bingham fluid, shear thinning, shear thickening, all are non-Newtonian fluid, so that doesn't follow the Newton law of viscosity. So I'll talk more in the next. So now here ideal solid where that velocity gradient is 0. So now here tau versus du by dy plot. When du by dy is 0, that is ideal solid, and tau is 0 but fluid is flowing, means 0 viscosity, that is ideal fluid. Now when that fluid the tau is directly proportional to du by dy, so that is Newtonian fluid. So n is 1. Yes, n less than 1, non-Newtonian fluid, pseudoplastic, and n greater than 1, non-Newtonian again, so dilatant fluid. And Bingham plastic, ideal plastic, so it has initial shear stress and then it will linearly increase, and another is another non-Newtonian fluid, so that is plastic fluid. Now example: pseudoplastic, paint slurries, dilatant, silly putty, quicksand. Bingham plastic, toothpaste, and plastic modeling clay. Thixotropic, certain inks, gels, and rheopectic, some drilling muds. Then coming to the vapor pressure, evaporation, and boiling. So vapor pressure is the pressure exerted by a vapor when it is in equilibrium with its liquid phase at a given temperature. It is a measure of tendency of a substance to evaporate. Vapor pressure increases with temperature. At equilibrium, the rate of evaporation equals to rate of condensation. Evaporation is the process by which molecules in the liquid phase gain enough energy to enter the vapor phase. It occurs at the liquid surface. It is an endothermic process as it absorbs energy from the surroundings. Boiling is the process by which a liquid turns into vapor throughout the entire mass of the liquid. It occurs at a specific temperature called the boiling point. Boiling is an intensive property and occurs when the vapor pressure equals to the atmospheric pressure. Then coming to the surface tension. Surface tension is the force acting at the surface of a liquid that tends to minimize the surface area. It is caused by the cohesive force between molecules in the liquid. Surface tension gives rise to effects like capillarity, droplet formation, and the shape of the liquid surface. Unit of surface tension. In the International System of Units, the unit of surface tension is Newton per meter. In that CGS system, dyne per centimeter. Now, what is the example of surface tension? Example of surface tension. So, water has surface tension of approximately 0.072 Newton per meter at the room temperature. The high surface tension of the water allows small insect like water striders to walk on its surface. Now, that application of surface tension and pressure drop. If you consider liquid droplet, for a liquid droplet in equilibrium, the pressure inside the droplet is greater than the pressure outside. The pressure difference del P is related to the surface tension sigma and the radius of the droplet r by Young-Laplace equation. Del P is nothing but 2 sigma by r. So molar droplet experience higher internal pressure. For a hollow bubble or soap bubble, similar to a liquid droplets, but for a soap bubble, the pressure inside less than the pressure outside. The pressure difference del P is related to the surface tension sigma and radius of the bubble capital R. Del P is nothing but force sigma by capital R. The pressure inside is inversely proportional to the bubble radius. Now liquid jet. For a liquid jet, the pressure drop is related to the surface tension and the radius of the jet. The pressure drop del P is related to the surface tension sigma, the radius of the jet and the angle of cone. So del P is equal to 2 sigma by R cot theta by 2. The pressure drop increases as the jet radius decreases. Next is capillarity, rise and fall. Capillarity is the ability of a liquid to flow in a narrow space without the assistance of external force like gravity. It is driven by the balance between cohesive force within the liquid and adhesive force between the liquid and solid surface. Capillarity action is observed in a small diameter tube such as capillaries or porous materials. Capillarity rise or capillary rise. Capillary rise is the upward movement of the liquid in a capillary tube or porous medium. The height of the capillary rise h is given by Jurin's law, that h is equal to 2 sigma cos theta rho g r, where sigma is surface tension, theta is contact angle, rho is the density of the liquid, and g is the acceleration due to gravity, and r is the radius of capillary tube. And capillary fall refers to the depression of the liquid level in a narrow tube below the level of surrounding liquid. It is observed when the liquid has a contact angle greater than 90 degrees. The height of the capillary fall h is given by Jurin's law. Same, h is equal to 2 sigma cos theta rho g r. Now condition for pure water and clean glass tube. For capillary rise, for a rise or fall to occur, the liquid must wet the solid surface. For pure water and clean glass tube, theta less than 90 degree, capillary rise is observed. For mercury and a clean glass tube, theta greater than 90 degree, capillary fall is observed. Now compressibility. Compressibility is a measure of how much a substance can be compressed or reduced in volume by the application of pressure. It is the reciprocal of the bulk modulus, mathematically expressed as beta. Beta is compressibility, that is negative of 1 by V dV by dou V by dou P constant temperature, where beta is the compressibility and V is the volume, P is the pressure and T is the temperature. And last, bulk modulus. The bulk modulus K is a measure of the substance resistance to the uniform compression. It is the reciprocal of compressibility, mathematically expressed as K is negative of V dou P by dou V constant temperature, where K is the bulk modulus, V is the volume, P is the pressure and T is the temperature. That's it for summary of fluid mechanics for fluid properties.